All right, let's jump right into this explainer. Today, we're tearing down the exact physics of how water behaves in soil. It seems pretty basic at first glance, right? Just dirt plus water. But the mechanics behind how soil grips that moisture and how plants actually wrestle it away is absolutely fascinating. We're going to build our understanding up step by step today, starting from those micro-level energy concepts all the way up to the real-world gear agronomists use out in the field.
So here's the game plan for this explainer. First, soil-water energy concepts. Then, components of water potential. Next, suction, tension, and PF. After that, soil moisture constants. And finally, determining soil moisture. Let's get to it.
Okay, Section 1. Soil, water, energy concepts. Specifically understanding free energy. Because to really get how water moves in soil, we got to get energy first.
Now, soil water is like anything else in the universe. It packs energy. It does have a little bit of kinetic energy, the energy of motion. But because water moves so incredibly slowly through soil, that kinetic energy is pretty much negligible. What actually matters here is potential energy. That's the energy something has just by sitting somewhere in a force field. Now, when you take that potential energy and mash it up with electrical, metric, and osmotic forces, boom, you get what we call free energy. Free energy is the ultimate boss of water's status. It's basically a measure of its escaping tendency. And the one golden rule you've got to lock in here, water will always, and I mean literally always, move from a state of higher free energy, think of a totally saturated muddy soil, down to a point of lower free energy, like bone-dry dirt.
So what's actually pulling the strings on this free energy? Well, it boils down to three main players. First up, matrix forces. This is the soil colloids acting like magnets, attracting water through adhesive and cohesive forces. Second, we've got osmotic force. That's the attraction of ions and other solutes hanging out in the mix. And it's super important to note here, both matrix and osmotic forces actually knock down or reduce the free energy of the water. And finally, gravity. Good old gravitational force. This is the big downward pull constantly dragging water deeper into the earth.
Moving right along to Section 2, components of water potential. This is where we break down those forces and actually put some math to them.
To figure out how water moves, we rely on soil water potential. Basically, how much work does it take to move soil water against these force fields, compared to just pure water at a baseline reference state? We calculate this using the total water potential formula. It's the sum of matrix potential, gravitational potential, osmotic potential, and pressure potential. Now, if this grand total is perfectly constant across the entire soil mass, the water is in what we call static equilibrium. No net force, no movement. But if that number isn't zero, the water is on the move. Let's break down each piece of the puzzle. First, gravitational potential. Gravity is constantly pulling soil water straight toward the center of the Earth. And since our reference point is usually set lower down in the soil profile, this gravitational potential is always a positive number. It's the exact reason water drains out after a heavy rain or intense irrigation. And thank goodness it does, because that's absolutely crucial for clearing excess suffocating water out of the upper rooting zone.
Next up is metric potential, and this is where things get really interesting. This comes from adhesion, so the soil solids physically grabbing onto the water, and capillarity, which is driven by the water's own surface tension. Because these forces are literally restricting the water and reducing its free energy, metric potential is always a negative value. Then we have osmotic potential. Just like matrix potential, this one's also negative. It happens because of solutes and inorganic salts floating in the soil solution. The water molecules start hydrating these ions, which completely saps the water's free energy. So osmotic potential is basically the work it takes to rip those ions away from the water molecules. Now, this doesn't do much to physically move bulk water through the dirt, but man, it plays a massive, prominent role in how plant roots actually suck up that water.
Finally, the wild card, pressure potential. This is the energy from the sheer weight of water itself, or even gas pressure. Unlike the others, this one swings both ways. Drop below the water table, and it's positive because of the heavy column of water sitting on top of it. We call that submergence potential. But get above the water table, and it goes negative because of capillary action. And depending on which type you're looking at, you'd measure it with an ordinary manometer or a piezometer.
Okay, so we've got all these negative potentials. How do we actually talk about them out in the field without making our heads spin? That brings us to Section 3, suction, tension, and PF, where we standardize the whole measurement process.
Since matrix and osmotic potentials are negative, agronomists usually just flip them into positive terms like suction or tension. It just makes the conversations easier. But back in 1935, a scientist named Schofield took it a step further. He introduced the PF concept. He defined it as this clever exponential function of the free energy difference. Specifically, it's the logarithm to the base 10 of the numerical value of the negative pressure expressed in centimeters of a water column. Sounds like a mouthful? I know, but it is a total game changer.
Let's put this into perspective and see how it scales, because honestly, it gets wild fast. Since it's logarithmic, tiny bumps in PF mean massive jumps in the actual water column height. Look at this progression. A PF of 0, that's just a 1 centimeter column of water. But bump that to a PF of 2, and suddenly you're at 100 centimeters. Hit field capacity at a PF of 2.53, and we're talking 346 centimeters. And by the time you reach the wilting point at a PF of 4.1, the tension is equivalent to an insane 15,849 centimeters of water column. The math just proves how fiercely dry soil refuses to let go of its last drops of moisture.
Speaking of field capacity and wilting points, let's hit Section 4, soil moisture constants. These are the essential reference points we absolutely need to make sense of everything. We need these milestones to practically tabulate our field data and figure out what water plants can actually access. Just look at this stark mathematical progression expressed in bars of potential. We start at saturation. Every pore is stuffed with water, tension is almost 0. Then we drop to field capacity at negative 1/3 bars. Keep drying out and we hit the wilting coefficient at negative 15 bars, the hygroscopic coefficient at negative 31 bars, all the way down to a totally oven-dry soil sitting at a staggering negative 10,000 bars of tension. No way a plant is getting a drop from that. So practically speaking, for field management, you gotta know where your soil behaves best. For medium-textured soils, there is a Goldilocks zone for tillage, right in the exact PF range of 2.8 to 4.4. This is the best tillage range to keep those small soil aggregates perfectly intact. Try to till wetter than 2.8 and you'll just puddle the soil. Till drier than 4.4 and the high cohesiveness means you'll rip it into massive clods and dust, completely wrecking your soil structure. Now, the two most critical constants you'll deal with out there are field capacity and the wilting point. Field capacity usually hits a couple of days after a good heavy soaking rain. The fast downward draining stops, the big macropores fill with air, but those tiny micropores, they are holding tight to the water and it's highly available to your plants. On the flip side is the wilting point. At this specific moisture level, the soil is gripping the water so hard that plants can't pull enough out to counterbalance their own transpiration. The plant shows wilting symptoms, and the real kicker? It cannot recover, not even if you put it in a 100% humid chamber. So, wrapping that specific idea up, plant-available water lives strictly, and I mean strictly, in the tension window between the wilting coefficient at negative 15 bars and field capacity at negative 1/3 bars. If the water is outside that specific window, it's either draining away way too fast or the dirt is holding it hostage. All right, let's bring it home with Section 5, determining soil moisture. We've got the theoretical values down perfectly, but how are agronomists actually measuring these exact tensions and percentages in the real world?
The absolute baseline is the gravimetric method. It's a super straightforward 4-step process. 1. Grab a fresh, moist soil sample from the field and weigh it. 2. Bake it in an oven at 105 to 110 degrees Celsius overnight. 3. Weigh that dry, crispy sample. And 4. Calculate the moisture percentage by dividing the weight difference by the oven dry weight. It's incredibly simple, but hey, errors can happen. If the soil's organic matter accidentally oxidizes in the heat of the oven, or if your sample cools down and pulls moisture right back out of the room air before you weigh it, your numbers are going to be off.
But obviously we have advanced methods that don't require baking dirt. Electric resistance use embedded gypsum blocks to measure connectivity. Though, quick side note, that totally fails if your soil is full of salts. Then there's neutron scattering. This is wild. It's a non-destructive method where fast neutrons are shot in, they crash into hydrogen atoms in the water, slow down, and are detected by boron trifluoride gas. Crazy science, right? Now, if you just want to measure tension directly in the field, you pop in a tensiometer. It uses a porous ceramic cup, though it tops out at a metric potential of negative 0.8 bars. And finally, the psychrometer. It uses a tiny thermocouple to find the total soil water potential by measuring vapor equilibrium in the ambient air. But what if you need to go past that negative 0.8 bar limit of a standard field tensiometer? Well, you head to the lab to extract the complete moisture retention curves. We use a pressure plate, which is essentially a heavy-duty lab tensiometer that can handle tensions from 0 to 1 bar. But if you really need to push the absolute limits, you bring out the pressure membrane apparatus.
This piece of gear can measure extreme energy-moisture relations up to an unbelievable 100 bars, and it does it in a very short time.
Wow, okay, we have covered a massive amount of ground in this explainer today, literally, from the core equations of free energy down to the exact hardware used to measure it all. So I want to leave you chewing on this provocative thought. Knowing exactly how soil water binds to particles in that highly critical window of -1/3 to -15 bars, how might these precise tension thresholds transform the way we manage field irrigation? Understanding this physics doesn't just explain nature, it empowers us to work efficiently with it. Thanks for hanging out with me for this explainer, and I'll catch you in the next one.